This is a continuation of Chapter 7, and this PowerPoint goes over how to calculate percent composition of a chemical formula and empirical formula from percent composition. So we're going to start with percent composition. First of all, it tells us the percent of each element in a compound. So if the compound you were talking about is natural gas, methane, it would tell you the percent by mass of carbon and the percent by mass of hydrogen. This is a very common way to express the composition, especially for consumer items. So if you go in the grocery store and you pick up almost anything and turn around the back, you will see pretty much the percent composition is how they tell you what all is in that. So here's the formula that we use to calculate the percent where X represents an element. And again, keep in mind that it's percent by mass. It is not percent by number of atoms, okay? It's percent by mass. So you start with the molar mass of the element that you're interested in. And then, of course, you have to multiply the molar mass by how many of those atoms of that element are in the compound. And then you divide it, since it's a percent, you divide it by the molar mass of the entire compound, okay? So, for example, let's say you were asked to calculate the percent composition of propane, C3H8. Now, sometimes you'll be asked to only provide the percent of a particular element. Like I might say, what's the percent of carbon in propane? But if you're just simply asked to come up with a percent composition, they want percent by mass of every element in that compound, okay? So again, here's the formula. So let's start with percent carbon. We know the molar mass of carbon is 12.01. Be especially careful in percent composition and empirical formula calculations to carry a lot of digits in your molar mass. Because just a little tiny change of a 100th in the 100ths place can cause a completely different percent composition or empirical formula. So anyway, we have 3 carbons in propane, so we've got to multiply carbon's molar mass by 3. Then the denominator, if you remember, is the molar mass of the entire compound, okay? Mass of the entire compound. And then since it is a percent, multiply by 100 as you do all percents. So the percent by mass of carbon in propane is 81.7. Now, the only other element in propane is hydrogen, so we can go through the exact same process, right? Hydrogen's molar mass is 1.01. However, there's another way to do it. Since there are only 2 elements in this compound, once you find the percentage of one of them, let's say carbon is 81.7, it's very easy to find the other one. We know that percents have to all add up to be 100, right? So 100 minus 81.7 is 18.3%. So I just wanted you to know that's a possibility. I have seen some questions on the standardized final that they'll be missing some vital information, and unless you think to figure out a certain percent composition by using the 100 minus percentages that you know, you wouldn't be able to figure it out. You might think to ask, why do we care about percent composition of a chemical formula? What's that for? Well, it turns out that a lot of the equipment we have for analyzing unknowns will give us results in the format of percent by element. And we can then, as you'll see later in this PowerPoint, take that percent by element information and turn it into an empirical formula and eventually the actual molecular formula. So I'll talk about the difference between these two formulas a little bit later in this PowerPoint. Look at doing that, okay? Here is an example. Okay, this sometimes is written, it's ethane, C2H6. Okay. you could be asked, let's say, what is the percentage of just carbon in this compound? So here we go. There are 2 carbons, right? 1, 2. Each carbon has a molar mass. I really should have carried an extra digit, 12.01. The molar mass of the entire compound is 30. And so the percentage of carbon in ethane is 80%. And here's one for you to try. I'm not going to work this out. If you're a student in my class, you'll want to go to Go Formative and show your work there. Alrighty. I did mention earlier that we can use percent composition information to get the empirical formula. So let's talk about, let's compare empirical formula and molecular formula. Empirical formula is the simplified version of the molecular formula. Think math, okay? So let's just say I had, let's go back to ethane, all right? That's a molecular formula. It tells you exactly, precisely, how many of each type of element are in a formula, okay? This is really what the material is. Now, the empirical formula is the mathematically simplified. So looking back at ethane, I could simplify those subscripts to be CH3, right? And so this would be the empirical formula. Now, why bother with empirical formula? Again, sometimes there's an analytical equipment that gives you the empirical formula, which if you look at it is simply the ratio of one element to another in a compound. And sometimes equipment isn't smart enough to know, that that's the empirical formula or not. It just gives you ratio of elements. So it's important for chemists to be able to work with an empirical formula. Now, of course, there are some cases where the empirical formula and the molecular formula are the same. So, for example, water, right? You can't simplify H2O anymore, right? So the empirical formula and a molecular formula are one and the same. All right, so this is a bit more complicated than percent composition, percent by mass. So this one, you may want to jot down, take notes, and you're going to have to practice a bit more, okay? So there are 4 steps to find the empirical formula from the percent composition. And this is just like a little ditty rhyme. I didn't come up with it, but it's nice. It works. So kind of sing it to yourself a couple times, help you remember it. It's just percent to mass, mass to mole, divide by small, multiply till whole. And it's kind of important. It's very common on an exam for students to leave out step 3 for some reason. So I'm going to walk through an example with you. Here's an example, and you can see the question gives you the percent composition of all of the elements. I'm going to show you how to take that data and get empirical formula. Okay, so you remember the first step, percent to mass. And all you need to do is take off the percent signs and change them to grams. So if you go back to that question, it said it was 61.31% carbon. Just literally take off the percent and put a gram sign, okay? And that, you can do that. We're not making believe stuff. All you do is you assume you have 100 grams total, okay, of the compound, and then that makes total sense. But anyway, switch the percent sign to grams. Easy peasy. Step 2, mass to moles. In other words, you need to calculate the moles of each. So this is kind of the same principle we've seen a lot, is you really can't, in chemistry, cannot compare one substance to another, be they elements or compounds, unless everything's in moles, okay? It's like trying to compare apples to oranges, as the saying goes. You have to get them all into moles before you can compare the quantity you have of each. So how do we get from mass to moles, right? We're going to do dimensional analysis, unit conversion, right? So if you're starting with grams, grams goes in the bottom. Our conversion factor is molar mass of carbon. And make sure in this step, because it's only step 2 out of 4, that you carry a bunch of extra digits along the way. Empirical formulas are picky. Okay, you have got to be precise at least to the hundredths place. All right, so that was step 2. What did step 3 say? Divide by small. This is a step that students tend to leave out and it messes them up. So make sure you always do this. So after you find moles of everything, you're going to identify which element had the smallest number of moles. All right. And if you look back a slide, that was nitrogen in this case. Nitrogen had only 0.7288 moles. So you are going to divide all of the mole values you just calculated by the smallest mole value. So we're going to take the 5.105 moles of carbon we calculated, divide it by 0.7288. See, here we divide all of the moles we calculated by the smallest mole value. Of course, the element that had the smallest mole value is going to be equal to 1, obviously. So now, the ideal situation is that all of the numbers you get when you do this, when you divide by the smallest, are very close to whole numbers. If you're lucky, and if you have an easier problem, that will be the case, okay? And that is the case here. And so the guidelines I tell my students is that if the number you get is plus or minus 0.1, it's okay to round to the whole number, okay? Okay, so if you had 7.1, it's okay to say, okay, that's close enough to a whole number 7. Same thing if you had 6.9, again, you could say, okay, it's okay to round that to a 7. Now, on the other hand, if you had 6.8, no, that is not okay. That is too far away. All right, so the actual numbers, when you get whole numbers, that gives you your empirical formula. So in this case, we have 7 carbons. Hydrogen, we have 7 hydrogens. For nitrogen, we have 1 nitrogen. And for oxygen, we have 2. So this is our empirical formula. That one was a pretty easy one. You just have to remember the steps. I want to take just a minute and show you what you do if you don't get a whole number. So let's imagine that we went through the first 3 steps for carbon, hydrogen, and oxygen. And let's say that you got 2 carbon, let's say got 2.06, okay? And hydrogen, let's say you got 2.33. And oxygen, let's say you got 0.33. All right. So carbon would be okay to round to a whole number 2, right? Remember if I said it was plus or minus 0.1, and that is. But hydrogen and oxygen are too far away from a whole number to safely round, okay? That's when step number 4 comes in that says multiply till whole. So what you're going to do when you have a situation like this is you're going to try multiplying by 2, and then you're going to try multiplying by, if that doesn't give you a whole number, you're going to try multiplying by 3. And if that still doesn't give you a whole number, you're going to try multiplying by 4. And I've never really seen having to multiply with a digit higher than 4 to get whole numbers. But you can't just selectively multiply 1 or 2. You have to multiply them all, right? Or otherwise you're going to change the composition. So let's try multiplying everything by 2, okay? So that would give me 4 carbon. This would give me 4.66. Ooh, that's not good, right? That's still too far away to a whole number. Same thing with the oxygen. If you multiply the number of moles of oxygen we have by 2, you get 0.66, which is too far away, all right? So let's go ahead and try to multiply by 3 and see what that does. So that would, let me do another line here. So if I multiplied carbon by 3, of course it's already a whole number, so you're going to keep getting whole numbers. That would mean 6 carbon, right? Now, if I multiply 2.33 by 3, what do I get? I get 6.99. There you go. That is close enough to round. And same thing with oxygen. If I multiply 3 times 0.33, I get 0.99. So in this situation, the empirical formula would then be C6H7O1. And as always, if you have just one of something, you can leave out the subscript, okay? So you will find when you work enough of these problems that if you get a fraction for an element that ends in 0.33 or close to that, or 0.66, you're going to end up multiplying by 3. If you get a fraction that's like 0.25 or 0.75, you're going to end up multiplying by 4. Okay? And if you get a fraction that's like 0.5, you're going to end up multiplying by 2 to get a whole number. So you'll get used to doing all that though. Here's one for you to try. And again, if you're one of Dr. Maffei's students, then you want to go to Go Formative and write in what you get for this answer. Here are the percent of each element in this mystery compound. So you want to go through those 4 steps and figure out what the empirical formula is. And that is it.